The water mining project is a Horizon 2020 research and innovation project. It is coordinated by the Delft University of Technology from the Netherlands and puts together 38 public and private partners and 4 linked third parties from 12 different countries across Europe. The project will develop innovative technologies for improving water desalination technologies, developing techniques for extracting phosphates and other bio-based valuable products from urban wastewater, and increasing circularity in industrial water use. This video is aimed at explaining Case Study 4, which deals with urban wastewater treatment in Larnaca, Cyprus. The water mining project aims to face the challenge of ensuring access to clean water and sanitation by developing innovative solutions for the sustainable use of alternative water sources, including urban and industrial wastewater and seawater desalination. The project considers water as a resource, consumable, and as a durable good. To capture the full potential of the circular water economy, the water mining project proposes different strategies for each of these 3 water forms. These strategies are developed in 6 case studies that involve urban and industrial wastewater and water desalination. Case Study 4 corresponds to one of the urban mining case studies. Larnaca wastewater treatment plant has a capacity of 100,000 population equivalent per day. Its average inflow is currently about 9,000 cubic meters per day, with its design capacity to be up to 18,000 cubic meters per day, while its maximum inflow could reach 20,000 cubic meters per day. From this unit, 2.5 million cubic meters of water and 1,500 cubic meters of sludge are produced per year, both used in agriculture. The specific objectives of Case Study 4 are the following. Demonstrate cost-effective removal and recovery of phosphate from the effluent of urban wastewater treatment plants or surface water to obtain ultra-low effluent concentrations. However, the salinity of the effluent is about 1.5 milligram per liter. Using water of this level of salinity could cause problems to the cultivation of very sensitive plants, while salt accumulation could cause land problems. Furthermore, water produced by the wastewater treatment plant has a 0.5 milligrams per liter phosphorus content. This concentration reinforces algae development in the lagoons, where the effluent stays before passing through the chlorination unit to the water supply system. The pilot of Case Study 4 is designed to treat this effluent, providing high-quality water which could also be used by industry. Moreover, this pilot design is based on circular economy, which means that the principle of zero discharge should be followed. Thus, sodium chloride and phosphorus produced from the effluent should be recovered in the form of valuable products, salts of high purity for industrial use, and a phosphorus solution that could be used in fertilizers industry. The current wastewater treatment plant in Larnaca has the following configuration. Pretreatment removes objects, fibrous material, and sand, which can lead to blockages of pumps and mixers. The next step is the biological treatment with carbon removal, denitrification, and enhanced biological phosphorus removal. Water is sent to the membrane bioreactor stage, which separates the activated sludge in an ultrafiltration process. This removes practically all particulate matter and thus further reduces BO2, total nitrogen and phosphorus. The final step is the disinfection of treated water, which is done with the use of chlorine produced in the plant. Sludge resulting from this process is thickened and mechanically dewatered. Then, it is transported by trucks to nearby greenhouses, where it is dried up to 70% for final disposal and use. The effluent from the membrane bioreactor will be treated at pilot scale bio-free installation with capacity of 1 cubic meter per hour, which will remove phosphorus in the permeate of the membrane bioreactor. Phosphorus concentration will be decreased from 0.5 milligrams per liter to 10 to 40 parts per billion. At these low levels of phosphorus concentration, biological growth is limited, biofouling in the membranes of the next system is reduced, and harmful algae growth in the intermediate reservoirs is prevented. This is followed by a process of nanofiltration and a low-temperature evaporator, which treat the effluent of biofree. First, nanofiltration will remove magnesium and calcium ions from the effluent. Then, the low-temperature evaporator removes salts of magnesium and calcium, around 80 milligrams per liter and 150 milligrams per liter, and recovers about 30% of high-quality water. Then, the flow permeates to the next treatment stage. The inflow to the reverse osmosis is 0.6 to 0.7 cubic meters per hour, with a concentration of sodium chloride of about 2%. There, it takes place a separation of monovalent ions from water, from about 0.42 to 0.49 cubic meters per hour, producing high-quality water of low conductivity. A condensate of about 30 to 40% passed to the MED, which condensates sodium chloride from about 7% to 19%, producing clean water. Then, the crystallizer condensates the MED effluent to a saturated solution of about 26% sodium chloride. Part of the sodium chloride saturated solution will be used in the chlorination unit. The rest will be used in industry. Water obtained from this process can be used for irrigation purposes or in the industry. The final products of this pilot will be phosphorus solution with use as a fertilizer, high-quality water, sludge, saturated solution of sodium chloride for the chlorination unit, and dry salt for industrial purposes. The system can be connected to solar panels, photovoltaics, and waste heat. It is fully automatized, so it is expected that few person months per year are necessary, mainly for supervising the operation of the system.